Hi, my name is Thomas Baker. I'm a student of Kieran Burke and Steve White at the University of California, Irvine. I have a guilty pleasure. I enjoy going online and finding cat videos and then sharing them with my friends on Gmail. The most embarrassing thing is that Google, the company that owns Gmail, definitely knows that I'm doing this. Collecting information like where I got the videos from and who I send the videos to is a goldmine for advertisers. But there are nearly 1 billion Gmail accounts. Collecting this information using a person just isn't a moneymaker. Instead, Google has designed a computer algorithm to collect this information. This process, called machine learning, is how Amazon knows what products to recommend and how Facebook knows who your friends are. Now, while I might be terrified of a machine collecting my personal information, there's also a lot of scientific applications that we can use machine learning to make our lives better. So, if a machine can learn my internet habits, can a machine also learn the fundamental patterns of nature? Machine learning, at its fundamental heart, is all about learning patterns. If, for example, I say 1, 2, 3, 4, you might say numbers or integers. As I said more numbers, the pattern became more clear. For another example, if you say 1, 1, 2, 3, 5, I might say Fibonacci sequence. Again, as more numbers were said, the pattern became more clear. For one last example, can you guess the pattern behind 12, 35, 45, 2, 57, 19? That's okay. I didn't either. These were last week's lottery numbers. The difference between the first two examples and the lottery numbers is that the first two examples had a pattern. The lottery numbers do not. We will never be able to design a machine learning algorithm to learn the lottery. But even more lucrative than winning the jackpot, we can understand the fundamental patterns of nature with machine learning. We already understand a lot of patterns in nature. For example, tossing a ball. This is a situation where Newton's laws apply very well. If we write down Newton's laws and apply them correctly, we can generate a set of mathematical equations whose solution is identical to the path that the ball takes. And that's the easy situation. If we look at small particles that are governed by the laws of quantum mechanics, the solution becomes much more strange. In my previous example, the equivalent would be if we take several balls and toss them all at the same time in different directions, blindfolded. And then when we take off the blindfold, all of the balls disappear except for one. While the interpretation that I just gave is based on mathematics and a little bit strange, we should believe the mathematical result. Quantum mechanics predicts experiments up to 20 digits in some cases. That's nearly unheard of in other sciences. So, while the interpretation may be a little bit strange, we should trust the results. And fortunate for us, there's only one pattern that we need to learn when we solve a quantum mechanics system. This pattern is exposed by rewriting the equations of quantum mechanics as a density functional theory. Once we do so, there is only one mathematical equation that we need to solve, and once we do so, we can predict anything: stronger, lighter materials, better medicines, better thermoelectrics, anything. The problem is that while we know that this pattern must exist, we do not know what the mathematical equation looks like. And that is where we want to use machine learning. In a machine learning algorithm, we can take a solution of quantum mechanics and show it to the machine. For example, we show it hydrogen. And then the machine takes that information and learns a little bit of the pattern. We then might solve uranium and give that to the machine, and a little bit more of the pattern is exposed. Then we give it the entire periodic table, and the pattern becomes very clear. We can then ask the machine, show me a superconductor, and it will simulate a superconductor with all of its wonderful properties. Whether we want to investigate the phenomenon of superconductivity, or we want to make flexible, long-lasting electronics out of carbon atoms, or simulate new materials, we can ask the machine learning algorithm in order to simulate these things. Right now, in history, we're sitting on a huge treasure trove of solutions of quantum mechanics. Placing them into our machine learning algorithm can allow us to investigate new, novel materials at a much faster rate than we are doing currently. We just have to show the machines the pattern. And wouldn't that be the cat's meow? Grr.